We are one of premium places, centers for additive manufacturing. Just taking that by industry expense. We have a very large center in additive manufacturing, headed by Mr. Surya Kumar, and we've done some really amazing work, including photos. 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 Another component. Manufacturing. So, if in comments, we can take you to see those facilities because we are a smaller subset of the larger India manufacturing process. President Panindra, of course, heads civil engineering department. We will also introduce the department to you. It's one of the most vibrant civil engineering departments in India. Then we have Professor Nagopal, who heads the CCP. And our CCP is very active in conducting a lot of courses for continuing education, for which we do get credit. And this particular course, the Gian course, is actually under the umbrella of so, with that, I believe you want to say a few words about manufacturing now. Think, thank you, Vives, and yeah, I wasn't prepared for this, and but I was prepared for this in my slides. So I will discuss a few on what are the facilities available related to additive manufacturing. I mean, mainly if you see additive manufacturing, we can at least have three active verticals or three active aspects working in in IIT Hyderabad. One is the metal, which I work on. One is concrete, which Professor KVLS is actually on this FDP. The other is also on biomedical. We also have a very strong biomedical and tissue engineering, tissue printing, etc. team also. Okay, so these are things which are going on, and it's good that we have its emphasis on the concrete. And I believe I also look forward to learning some on these details in the coming. All right, thank you. May I ask Professor Fanindra to say a few words about the department? We have a video, but I think it's old. So you'll have to go extempore.
Okay, sure. Personally. So, on behalf of the Department of Civil Engineering, welcome you all to the department. This is one of the largest departments of the institute, where we have 30 faculty working in 5 different specializations, ranging from structural engineering, geotechnical, water resource engineering, environmental and transportation engineering. We have about 470 students. The predominantly our emphasis focuses on research, where our PG strength of its masters and PhD in combined is larger than the undergrad strength. Actually, that's actually one indirectly tells actually the focus or actually the intention actually that we have towards research. Also, the fact that the department, though it's actually called as a second generation IIT, uh, keeping the numbers aside in terms of the quality, like the number of the publications per faculty or the number of citations per faculty or the H index of the departments, were in the top 3 civil engineering departments of the institutes of the country. So the faculty are really working in diversified domains with research fundings from various both government and private agencies. And also faculty are heavily associated with interdisciplinary programs. We also faculty are also leading the centers like TriHub, Center for Sustainability, Tihan. We are actively associated and also associated with other departments like climate change, heritage science department, and so on. So again, welcome. Probably you know actually the kind of structure that we have: a steel facing and the concrete, the back, and you are free to uh, go and explore the lab facilities that we do have. And of course, the faculty and the staff will be there always to see if you need any support actually, or if you just want to explore the facilities, we are happy to go ahead. So with this, actually, I thank you, Professor Kibilis, and hope this course goes success.
I guess the video on CCE started before. I wanted the institute was there. So anyway, let this play. So because anyway, the next guest that I'm going to introduce is Professor Rajagopal, who's the head of the CCE. We have a fantastic convention center, and that is something that I think Professor Rajagopal will introduce.
Yeah, so very good morning to all of you. So on behalf of Center for Continuing Education, I welcome you all to this course. And also on behalf of the center, I welcome our distinguished speaker, Professor Narayanan, who has agreed to be part of this Gian program. And at Center for Continuing Education, we are aiming at offering programs for training academicians, students, working professionals, researchers, and scientists And the IIT Hyderabad has very young and dynamic faculty, where the average age is about less than 40 years. And they are very active in providing training programs for uh, various spectrum of students, working professionals, and researchers. So we have different types of certification programs, short-term certification programs, which are less than 4 weeks, and long-term certification programs, which go from 1 month to almost 1.5 years. And we offer certification programs in terms of PG diploma programs and also online MTech programs through Center. And with e-learning catching up, we are also offering a lot of certification programs with third parties who are collaborating with IIT Hyderabad, especially in the areas of artificial intelligence, machine learning, cybersecurity, and data analytics. We have very popular courses. Apart from other core engineering disciplines, we are also offering several other online programs. Most famous of all is called Open to All Teaching, where all the courses of IIT Hyderabad, based on faculty interests, are taught in an online mode. And anybody across the world can register for this course at a very small registration fee. So it is in the broader initiative of the government where the country wants to be like a Vishwa Guru, where we can offer education to all. And we are also offering several online courses in the Swayam platform, which is the regular NPTEL courses. Several of our faculty are involved in teaching the NPTEL courses. So there is a lot, and we conduct a lot of workshops, conferences. The teaching and learning cell at IIT Hyderabad is very active, and it's engaged in several faculty development programs and in training teachers. So for the first time in the country, we have a center called a Center for Research in Education and Teaching. So it's called as the CREATE, and so we are working towards doing research in teaching methodologies and in education. And the TLC is very active in doing several faculty development programs for school teachers. So we have done until now about 5 or 6 batches of training teachers in Jawahar Navodaya Vidyalayas, Kendra Vidyalayas, and other schools. And coming to this course, I think this is one of the most needed courses on additive manufacturing, and we have the best faculty here. Uh, and Professor KVLS is our one of the first faculties who started this department at IIT Hyderabad, and he was our first head of the department. And also, if when you enter this campus, you see that campus has grown so much. Unlike most other IITs, IIT Hyderabad has been very uh, beneficiary of having a very excellent campus. I think a big round of applause goes to Professor KVLS for designing this campus, which is almost, if I'm correct, about 575 odd acres. And every aspect of design was done by discussions with Professor KVLS, and his meticulous involvement has brought the campus to this shape. And he is amongst the top 2% scientists as per the Stanford rankings, and persistently for last 3 years, not only annually but also career based. That it itself speaks volumes about the research that he's taking up. And we are lucky to have a professor like Professor Subramaniam to start our department and to mentor us all through in the last 15 years. So I think a big round of applause should go to and then he is an excellent teacher. You can know in the next few days you have the opportunity to listen to him. There's one thing common between me and him, that only one thing common, that we both joined at the same time. He was a full professor, but I was the assistant professor, and he did mentor me over the years. And And then there's a lot of, with his guidance, as Professor Fanindra said, uh, the civil engineering department has shaped up in a very nice way. We are the most active and most richest department in IIT Hyderabad. And I'm also in charge or lab head for structural engineering. So there is a video I saw about structural engineering. I invite you all to visit our labs. Right, we have one of the excellent facilities for structural engineering, and we have a state-of-art facility for material testing, which is developed by Professor KVLS. Apart from that, we have a very excellent lab in structural engineering. I invite you all to come and visit our labs. And Professor Narayanan is an expert in an area of additive manufacturing. I think it speaks volumes when you look at his profile and his publications. I think it's a great honor to have him here. I think you are all privileged to be part of this Gian course. I request you all to make best use of this opportunity to learn. Yeah. Thank you.
I think Raja has done enough to embarrass me, but now it will be a tough act to follow. But since we're tooting our own glory, we thought we'll show you, and you can have those sound as well. We'll show you about IIT Hyderabad. Uh, yeah, sorry guys, it's the stage. So we have a very unique campus. To take this opportunity to go around the campus, see all the facilities that we have to offer. This is a campus that has drawn inspiration from Stanford in its design, and so you not find such buildings anywhere else in India, at least. Every building is unique, designed for a specific functional need, designed to architecturally inspire its own domain. There's an excellent sports facility, which is on north side, further away from the hostels. We've also invested very heavily in research. So we have this center for, we have a center on Tihan, which is for autonomous self-navigation, the only one of its kind in India. And it has large fundings from Google, Suzuki, and I forget one more company. This is on campus. It's India's first 3D printed bridge. Um, Then we are setting up a school of sustainability, the Greencoat School of Sustainability. We are the only school institute in India to have a department for innovation. We are pioneers in 5G, 6G technology. We hold the most number of patents in this upcoming technology. And we have a very active trust in sustainable infrastructure. So the entire structures group is involved in it. This is a one of its kind center in India. We're to set up on the funding from DST. It's a 200 crore center where we are the only institution in India to have an atom probe microscope. We have an incubation facility, which was initially started by Professor Surya. And these are our statistics. Right from the beginning, innovation and invention has been the two key factors that have driven our growth. So we say IITH is innovating and inventing for humanity. So thank you for your patient viewing. We have another longer video on structural engineering group. I promise I'll play that after the break. At this point, I want to conclude on the inaugural session. I'd like to invite Professor Narayanan just to say a few words. I know you'll hear from him throughout the week, but just a few words. Embarrassing. No, thank you. I think I'm already embarrassed.
Good morning, everyone. Thank you to IIT Hyderabad. Thank you to CCE for organizing this course. Extremely happy to be here. You will hear from me for the next 5 days. So very happy to be here. Very happy to see all of you. It's going to be an interesting course. Lots of lovely things happening in IIT Hyderabad. But just to tell you quickly about where I come from, of course, I know Professor KVLS for 25 years. We've been doing work together, lots of different things. But I'm at Arizona State University, which is the largest public university in the United States with about 125,000 students. So it's all about scale. You have a school of sustainability. ASU has the first school of sustainability in the world, and we have it's ranked number one in sustainability all over the world. Lots of buzzwords also. Like you see all sustainability everywhere. But we have a rich, vibrant ecosystem. So if you are in the US for something, come visit us. Lots of interesting things, lots of exciting. ASU is all about scaling education, scaling research, scaling infrastructure. So again, 125,000 students in 4 campuses in the Metro Phoenix area. So huge place, lots of exciting stuff. And this campus is amazing. If you've seen, if you walk through, I've come here 3, 4, 5 times now, and every time I come, things are changing, new things are happening. So happy to see all of you. We'll see you over the next 5 days. We'll talk more about concrete 3D printing, additive manufacturing, and welcome to this course. Thank you.
Okay, I think I'd like to wrap up on the inaugural function here. We wanted to keep it very simple. Thanks to everyone for joining. Really appreciate your inputs and help us get off to a flying start. But before we let them go, I think no good deed should go unpunished. So we have to punish I guess. Yeah. Thank you. We'll spare you the blind. I know you want that. You'll get it on the way. Yeah. Surya, okay. Not treating you like a guest, but just sure. Thank you. Okay. Put down. Narayan, there is a plant and take it out. Yeah. No, We've already did it. Okay, so thank you, everyone. Just a few notes before we get started. I think, yeah, I'll get you off your high chairs here. So, should we do the group photo now? Yeah. Okay. We'll assemble because before they all disperse, we'd like to take a group photo out on the stairs. But before we break for there, a few general notes. I know most of you are set up in the hostels. We apologize for this. Unfortunately, there's a big event, or fortunately, there's a big event happening on campus. So all the accommodation is taken up. We've tried our best to make you comfortable in the hostels. We hope you can bear with it. Then in this building, we have the washroom facilities on either side of this room here. And the civil engineering department, all the offices are in the steel building. If you would have realized, this is basically a two-part building. The concrete building is where we are located. All the labs are in this building. So we'll have one lab session that we planned on the 3rd floor here, just above us. Then one lab session is planned in the heavy labs, which is basically just a stone's throw away, but it's a separate building. We are planning a field trip to a production facility where they're actually producing. This is a company that I collaborate with, I work with, I mentored them. And they use a robotic, they developed their own robotic arm printing system. So we are planning a field trip on Friday, if everything permits. Otherwise, the lecture schedules are we've given them to you with your registration kit. We'll strictly try to follow the lecture schedules. And I think Narayanan will set the ground rules as we get going. Now, we will try to do as much hands-on as possible, but then with a group of 40, it may not always be possible. So we'll try to do demonstrations at least for a lot of these trials and other things that we are planning. Okay. So anything at all that you need, any questions, concerns that you have, you already have the contact numbers of Spandana and Prashant who've been in touch with you. We have other student volunteers in my group. We also have 4 students from Arizona State who also agreed to volunteer. They have not, then I'm already drafting them into service. So they're also here. So yes, look forward to having wonderful 5 days with all of you. Let's make this a good learning experience. So let's all assemble on the stairs here. We'll take a group photograph and then we'll reassemble for our first lecture with Dr. Sudhir. After the fine. So we'll just take a photograph, then we have to rearrange that. Okay. and the overall background of the manufacturing. We all think it's 3D printing, but we have realized that 3D printing is a colloquial generic term. The technically accurate term is additive manufacturing. And what better way to learn but from an expert? So I think we get the lecture started if your mind.
I think they have, yeah.
Oh,
Ready now? Good. All right. Okay. So this is not a mic. This is only a microphone. Okay. So that means you will still hear me directly talk. And this is a small cozy classroom. So I hope I am audible and clear. Okay. But if you are facing any difficulty, let me know. Okay. Done. Okay. So good morning, everyone. And I think we were supposed to. I was supposed to give you some headache and then have tea. But I think my 5 minutes itself was enough for you to give a headache instead of my 1 hour. So anyway, I think here we go. So my name is Surya. I think it's kind of my standard slides. So I'm a little odd man out here. I am not a civil engineer. I am from mechanical engineering background. Okay, and I work a little on polymers, metals, etc. Not so much on concrete, but I do think kind of just give you a overview of what we are looking at. So, kind of, I think we all know additive manufacturing, 3D printing, etc., etc. People keep talking about it a lot. Okay, but what is the core concept that it differentiates additive manufacturing from other processes? So, for example, there are a lot of manufacturing processes, fabrication processes. There is a high-speed machining, there is a nano machining, there is a ultrasound machining. There are tons of other different, or there is, okay. By among all these processes, 3D printing or additive manufacturing captures the imagination of the general public in a higher magnitude than the rest of them. Okay, and you can see essentially it's not that this is the only, and just to gauge it, you look at the number of conferences you have. Just look at the conferences, titles of the conferences we have in IIT Hyderabad, let us say. Okay, and look at them. Only 1 or 2 of these capture the popular imagination. Of course, AI, 5G, etc. But when it comes to actual fabrication, additive manufacturing is only very few of them. Additive manufacturing being an exception in that regard. So why is it that it captures so much of popular imagination, so to say? And what is that which differentiates additive manufacturing from other processes? Okay, so that's, I think, the broad idea. So if you see traditional manufacturing by and large, okay, so naturally I'm giving more workshop kind of examples. Okay, so you have different shapes, casting, forging. Okay, the idea is you have a different fabrication method for a different shape. And I think that concept even holds true in concrete and civil engineering also. You have one particular methodology for straight walls, you have one for curvilinear walls, you have one for dome structures, you have one for, okay. So the idea here is your manufacturing process is dependent on the shape or geometry of the process. So it is nothing like you go to some workshop in charge or some civil engineer and says, what is my best manufacturing technique? The first question he or she will ask is, show me the geometry. Then I will advise you further. Okay. 3D printing is the one. That means the idea here is fabrication, the traditional sense, requires you to be an expert of the domain. Okay. You have to have basic familiarity of what is casting, welding, forging, lathe, or equivalents in other biomedical or civil engineering context. Okay, you need to be a thorough background expert on various aspects to do actual fabrication. 3D printing, on the other hand, actually inverts it. Okay, so kind of, I mean, I think we keep joking. It is manufacturing for duffers. Okay, what we mean here is it is a process which does not require any prerequisite from the user to fabricate. You can, in fact, I mean, that's true. Even school children are fabricating stuff. They're fabricating robots. They're fabricating even your flower pots also. Fine. Okay. I mean, extremes. So you can have a nice flower pot design. You design it for your home, okay? And you don't have to go to a injection molding or a plastic industry. You can just 3D print it. You don't need a background of the manufacturing processes to do that, okay? So kind of, I think that is the whole idea. Is 3D printing allows you to translate from untrained, fully trained to untrained users also can use it. Okay, so I think that is one of the reasons why 3D printing captures a lot of this imagination in the public eye. Is it kind of, I mean, it can be fabricated with no background in the fabrication methods. So you can just go to Amazon, buy a 3D printer for 15,000, 20,000. It's actually available in Amazon. You can just order, you'll get it in your hostel room or your house. Okay, you can start printing and you can make stuff which you like, design. Okay, with zero background in manufacturing, you can do that. Okay, that's essentially the idea. Why it is fascinating for people is because not of the technology per se, but of this idea that even non-mechanical engineering people, non-civil engineering, non-experts, school kids even can do 3D printing, can fabricate and use it. Okay, so that's kind of the basic idea. That doesn't mean that our course here is redundant. Okay, I mean, अगर school बच्चे कर सकते हैं तो हम क्या सीखेंगे type. Okay, I mean, that's not the question here. Our role is to facilitate that journey. Okay, our role as experts. Okay, that is the aim of the 3D printing, but it's not there yet. It's not fulfilled yet. And our role as experts working in this domain is to facilitate that journey. Okay, so our facilitate, for example, is kind of even your mason can think of 3D printing. How to, so it's not just engineers and robotic operators who can do concrete 3D printing, but even how do you simplify it, for example, for a normal mason also to handle and do your work in easier manner. Okay, so that is the interfaces, the technologies, etc., which you have to keep building. Okay, so kind of, I think before I go into how it does that, okay, so that's the idea, how it does that. Before I go into it, kind of look at what it can do. So there are a lot of things. So for example, this is one of my favorite, so it's just a simple shoe design, but it's as if somebody is literally holding you, uh, holding your weight, okay, or the jewelry. Okay, so in fact, the highest number of 3D printers, when I was in Mumbai, the highest number of 3D printers were not with IIT Hyderabad, unfortunately, were not with IIT Bombay either. It was with the jewelry cluster. Okay, there is a jewelry consortium in Mumbai. Okay, and they had, I think it is still true to certain extent, I'm not sure about the current numbers, but they had almost the highest number of 3D printers in the Mumbai region. Okay, so there are even other applications also. So what you do is, these are this fancy. Okay, so generally idea is, if you have a new technology and you are looking for customers, this is typical startup talk. Okay, if you have a brand new technology and if you need new customers to take this, there are only three people you can go. One, defense people, because naturally, I mean, I think defense takes priorities and okay, you don't mind putting the money. Are the biology people, naturally, because human life, you cannot put a cost to the human life, and any cost is this thing. And the third is the kind of wealthy hobbyists. Okay, so for example, if I tell you that, look, this is a ring in some XYZ jewelries, if I purchase, okay, and the gold rate is so much, so fine, okay. But if you say, look, this is your wedding ring, I'm going to sit with you, and this is the most unique print, you will design it and you will make it, okay, and even I can have your own thumb impression or some voice recognition, etc., imprinted on it, etc., etc. I'm pretty sure most of you won't mind giving some double the price for that ring. Okay, so these are your typical three customers. Okay, and I think 3D printing today, of course, caters to those kind of people also, or those kind of community and industry also. Okay, so we are not cost effective yet. Okay, we are either very niche applications which cannot be done otherwise, defense and biomedical, where there are no other alternatives, or where you kind of, you want uniqueness in or personalization in what you're doing. This is your typical market today for these kind of applications. Okay, so I think the same corollary happens. Okay, so for example, IIT Madras has 3D printed a post office, if I remember correct. Okay, पोस्ट ऑफिस तो इवन कंटेनर से भी बन जाएगा. Okay, if you want to get that utility done, okay, even you kind of take a container and cabins, etc., you can create the job done. Where they're doing it, not for the utility purpose per se yet, okay, but maybe the vibe value of it, okay, the uniqueness value of it, okay. But I think it's also that's the starting point. But as you grow, even uniqueness things which cannot be done by other means. For example, I think Professor Kevilas is also working on bunkers for soldiers in difficult terrains, etc. Okay, where it's not just it is good to have, but where there is no other alternative existing also. Okay, so those are the things which applications you are looking at. So also you have, for example, you have 3D printed skin today, 3D printed, people are talking, already my colleague Falguni in biomedical works on 3D printed cornea already. So they are working together with LV Prasad and doing it. And people are talking about 3D printed kidney, liver, etc. also. And 3D printed skin is already a reality. There are even dedicated 3D printed costumes, fashion shows which happen. Okay, so and of course in architectural applications, the make and feel of the buildings, etc. And you even have, for example, there used to be a website in US based website. So where you go, you upload some 3-4 pictures of it, then they will make a miniaturized version of it, 3D print it in their 3D printer, send it to you by post. Okay, so you don't even have to own something. Okay, or literally this somebody kind of so typically the idea is chocolates and roses go together. Okay, so kind of particularly when you are proposing to someone. Okay, and this fellow literally combined them literally. Okay, so 3D printed chocolate. Okay, in a rose form. Okay, so you can, all 3D printing allows you to do all these things. Okay, and you also have a lot of hype. Okay, so kind of I think so you see people talking about the third industrial revolution, the fourth industrial revolution, and all this. Okay, and frankly, we are researchers, so we are not salesmen. So this is actually hype. Okay, so 3D printing is not going to replace any of your conventional methods, conventional processes, conventional technologies. They are going to augment it. There is enough space, there is enough for everyone. Okay, and I think 3D printing will add a lot of value, but there will be a lot of places where conventional techniques and methods will have their method, will have their preference, have their advantages. Okay, so I think A replacing B and all is a salesman talk. I don't think that's real. Okay, what we have is an expanding market and the expanding pie, and 3D printing getting a big part of that pie also. Not at the cost of others, but rather in collaboration and in sync with other processes. Okay, so that's kind of how we look at it. So now coming back to that question, how it happens, how does it do that? Okay, so typically the idea is like your Lego bricks. Okay, so you have a set of Lego bricks. The same Lego bricks, you can build a castle, you can build a tower, you can build a bridge, you can build no matter what. Okay, so the idea here is look at a shape not as a single object but a sum total of repetitive elements. Okay, so essentially once you start looking at it, all these things get simplified. Okay, so kind of I think for example, this is a hollow cylinder. Okay, but look at it like each element. Okay, you add each element into your place. Okay, and that's how you kind of build it. Okay, so on the same set of coins can you can make a pyramid out of them, you can make a wall out of them, etc. So and I think again the example of it, understanding of it is also from the 2D printing of it. So if you remember the old style 2D printing, block letters, typesets, etc. How 2D printing was revolutionized is basically, once you stop looking at it as alphabets A, B, C, and started looking them as dot matrix, then the whole 2D printing has got revolutionized. Earlier, you have one type of block sets for Times New Roman, for 16 size, for 18 size, one for English, one for French, one for Japanese. Okay, so you had dedicated sets for each language, for each font, each size, etc. Okay, because you are looking at a, you are looking at a B, etc. What you are doing is actually discretized. Just there is a point there or there is no point there. That's it. Okay. The moment your approach to things have transformed in this manner, the whole 3D printing revolution has been made, 2D printing revolution has been made possible. Okay, dot matrix printers. Now, you really don't care block set, etc. The same printer can print all different fonts, all different languages, all different texts, etc. Okay. So similarly, the same is the idea with 3D printing also. Don't look at it like a axisymmetric component, a dome component, a flat component, a walled component, etc. That is how we look at it. As long as you look at these as shapes, you will have a specific method. You look at it in a more generic manner, 3D printing then helps you do that. Okay, so that's kind of the approach you're changing. So the idea here is you take any shape, divide them into multiple layers, okay, and realize each layer at a given time. So whatever you're doing, you kind of discretize it into basic shapes or basic layers and realize them one at a time. Okay, so that's the philosophy behind how 3D printing works. Okay, so this is an example. Okay, so you see, I've taken a simple rope. The same rope can be stitched together in the form of a cup, in the form of a basket, etc. Okay, the element is same, but the pattern you're making it go will result in what shape you're getting. Okay, and that is essentially how 3D printing can help you in different shapes, different etc. Okay, so kind of, do you recollect any example of such a thing? Okay, so you see that example of Hanumanji going to Lanka and he was not offered a chair and then he makes a chair out of his own tail, etc. Okay, so the idea here is that our approach is similar. Okay, only he just uh, not divine enough, so he'll just use computers to do the job. Okay, but the idea is that you have a element here, basic entity, which is a rope. Okay, and the pattern of the rope is what is giving you that shape. Okay, and I think it's also a good corollary. There is also a matching story in Mahabharata. Okay, where Bhima and Hanumanji, when I mean, so the same tail becomes a chair in Ramayana, and the same tail becomes a wall in Mahabharata in that Bhima encounter, etc. Okay, so the object is same, but the shape is different. Okay, so that is what we concept of what we are trying to do here. Okay, so how it is done? Okay, so kind of I think this is a simple video of actual 3D printer, a plastic 3D printer in action. Ten marks for persons who guess what is the shape being made earliest. What is the object being printed? No, thought of, I mean, related. Huh? Yoda. Okay, yeah. So from the Star Wars, Yoda. Okay. So the idea here is, you see, if I think of traditional manufacturing methods to do such a thing, okay, I create a CAD model, I make an injection mold out of it, okay, permanent molds, take a block of this thing, remove the metal, okay, then I do injection molding into it and then I make it. Now you see how simplified the whole process is. And why was it possible to be done? Because you're doing it in a layer by layer manner. You don't really care what is the final component. All you are interested is one layer at a given time. Okay. And this layer concept, I'll show you even some other examples also. Okay. These are time-lapse videos of different shapes and geometries. But the idea here is you can see that very complicated shapes are addressed by simply going by layer fashion of fabricating. These are all in the YouTube. You can just, search them and okay. Why it is important to remember the time lapse is 3D printing is not fast. Okay, it takes so whatever is that Master Yoda you have seen takes 4 hours or 5 hours in the lab to do. You can look at the clock behind. Okay, but you can see the simplicity of the structure here. Okay, while such a pyramid, it's a fractal pyramid. Okay, so such a fractal pyramid is a manufacturer's nightmare. Okay, because there are too many overhanging features, too many output, input, etc. Okay, so this kind of a shape is a manufacturer's nightmare. But you can see they have, by making it layer by layer, it has so easily able to achieve it. So different shapes again. So this is another kind of a complicated crisscross structure. You notice the amount of cross-linking and cross-channels which are happening. Now imagine your traditional method. What would you do? Typically the structures, you will take different pipe elements, you will try to cut them across, you will weld them together, etc. Okay, and a nightmare job at it. Now what this has, it does not really care what is the geometry. At a given layer, it is just some 10 different circles it has to deposit. Okay, that's all it cares. Okay, so any complicated 3D geometry, by making it into lot of 2D geometries, it has made it very easy. Okay, so what it has done is discretized it a 3D into a 2D, just like our printer discretized words into dots. Okay, so converting them into binary dots, you are able to achieve any shape. So similarly here what they have done is converted a 3D into numerous number of 2D elements, and you're able to then take up any shape, any geometry, very complicated ones, and easily achieve it. This is another more examples. Okay, so again I think easy examples of different shapes. So one thing you can notice it is the machine does not really care about the geometry by and large. I mean, there are ifs and buts. That is what this next 5 days are going to be. Okay, but broadly speaking, the machine does not care about what is your geometry. So it's like, one machine for all type. Okay, so typically you have a axisymmetric, a lathe, a vertical machining center, a horizontal machining center, a drilling, a boring. These are the various ways in which you fabricate. This machine does not care. Any shape, same process, press input, remaining things, the computer does it for you. Okay, so I think I was playing this video and somebody did ask me, sir, you kind of 3D print guns, is it not a security issue? Is it a security issue? Huh? If I 3D print a gun, is it a security issue? Because actually the crucial part of the gun is the bullet, the gunpowder, okay, not the gun, okay. As long as the gunpowder is controlled and the bullet is controlled, it is fine. ये gun तो क्या है? I mean, you give me a pipe and I will make a guncha out of it. Okay, so I mean, if you have enough, you give me a kitchen pipe and you give me a file, I'll make a gun out of it also. Okay, so That's not the tricky part of it. The tricky part of the gun is the bullet. Okay, as long as the bullet is controlled, you're fine. Okay, so these are just toy guns. Okay, so that doesn't really matter. So there are different things which you can do. Okay, so I think stop there. Okay, so it goes on. Now the thing about it is it's not a single process. We have a complete master's a MTech program in additive manufacturing. Okay, so that means there are a lot of things than whatever plastic I have showed you. So there are some, these are different variants of 3D printing. Okay, what is common to all of them is each of it is sliced and you are realizing each at a given layer. Okay, so there may be different, but what may be different is sometimes you may use a sheet or a liquid or a powder or a wire, different raw materials. You may use a binder or a laser or a electron beam or a photopolymerization. So how you are fusing them and how you are getting the raw material can vary, but the concept of going layer by layer is same. Okay, that's also one of the reasons why additive manufacturing is also referred as layered manufacturing in many instances. Okay, so this is what is common. We go line by line, layer by layer is how we go. Okay, now based on various processes, this is essentially ASTM uh, categorizes them into 7 methodologies, generic methodologies. What is called as sheet lamination, material extrusion, wet polymerization, powder bed, etc. So these are the various formal ASTM categories of additive manufacturing, 7 of them. So what I will do is kind of run across all this one by one. Okay, and I think the intent of the lecture is to only give you a glimpse. Okay, so don't mind if I am running little fast there. Okay, so because just the idea is to give you a holistic map of what are the various technologies and possibilities in it, not to make you masters in this 1 hour of that. Okay, so that, but the idea is you know the keywords. If you want to learn more of them, you at least know what to search for. Okay, so the problem today is not lack of so kind of how we tell is you have Google, you have this AI tools today, you can get all the informations. What is that we are trying to do is give you the right keyword and helping you phrase the right question. Answer is there. You just, I mean, the problem is too much of information, not lack of information. Okay, and here are your Google searches. Okay, that's what we are doing. So this is kind of, I mean, the 7 categories. Let's go one by one. So the first method is what we call as sheet lamination. So the idea is simple. वो जो सावरकर जी का कहानी है ना, okay, I mean, or you have your shorthand redemption. Okay, so the idea is you can create a 3D shape by cutting 2D layers, 2D papers and stacking together. Okay, so if you actually look at it, it's a 3D element, but it is one page at a time, one cut at a time, another page, another cut, another page, another cut. Okay, and you stack all of them together, it becomes a 3D. That's exactly what you are going to do in your layered manufacturing of the first method, sheet lamination. Okay, so what you do, you take a sheet, you cut the elements, whatever it is. Okay, then paste another sheet, another sheet. So you're essentially doing one page, the shape of that shape page, bond it to the next shape, etc. Okay, so let me show you the video of it. So this is the idea, is you have a laser and you have a paper, and the laser is cutting the paper in the desired shape or desired outline. And then you have again a binder roller, you're putting another layer of paper. So you go on building uh, pages. Okay, you're just accumulating pages. And finally, once you're all done, you have a block. Now you remove all the unnecessary paper material around it. Okay, and then you have your final shape. Okay. So how is this shape formed? You're just formed by cutting different pages or papers and stacking them all together. Okay, that's kind of your basic sheet lamination method. This is kind of how the actual process looks like. You have a laser cutter cutting the paper. You can see the fumes, etc. Also. Okay, that's the basic concept of how it works. And you kind of what you do is this is typically how it looks like. So what you have done is this is the geometry, but it is hidden under a bigger sheets of paper. You remove all the unnecessary stuff and you have your final geometry ready. Okay, and this is achieved by stacking together multiple layers of paper or polythene, whatever it is. Okay. So some of the examples are these kind of large components can be easily achieved. Mostly they are used for your casting patterns, etc. Okay, so you can also notice the little brownish tinge because you are burning the edge of the paper. Okay, it gives a little wooden feel into it. So these are different geometries you can manufacture. So anything special about this geometry? This is of course also made through the lamination sheet lamination process. It's a revolute joint. Okay, so it's one of the things. Irony of it is it is an assembly which is not assembled. Okay, typically it is an assembly of components, right? I mean, and the whole idea is assembly means assembled. Okay, so here is a component, a assembly which is not assembled. Okay, so 3D printing is one of the few options you have where you can create such complicated shapes and geometries. Okay. The second methodology is the material extrusion. This is generally the most popular version of 3D printing, material extrusion. If people don't specify 3D printing, default it is assumed that it is material extrusion FDM version. Okay, that's kind of the most affordable, popular in numbers, in costs, etc. also in the community. So this is what it has. Okay, so literally my teacher used to say it's like jalebi making. Okay, so what do? You take a batter. Okay, you move it. Okay, and the moment it comes out, it solidifies. Okay, so that's essentially what is happening. And the shape of your jalebi is determined by the shape of the direction in which you move the batter. Okay, so if you want a small circles or a big circles or a square ones, is dependent not on the batter but the direction of your hand. So similarly, the shape you get is actually dependent on the shape of the nozzle which you are moving. Okay, but what happens is a hot plastic is pushed through your nozzle and it comes down extruded. Okay, so typically this is what happens. You have a raw material in the form of a wire which is pushed across. Okay, and you have a hot nozzle. So you can see the plastic getting into the molten state. Okay, and in that molten state it falls onto the base plate, and because it is falling on the molten state, it also joins together with the previous layer and then binds together. Okay, so that is how your typical 3D printing plastic FDM printer works. So this is just another video of it. Okay, so this is kind of how you can visualize the object. So you see what is happening is from the nozzle you have molten plastic being extruded out. Okay, and the way you are moving the nozzle will define the shape it is getting. So you can go on like this. So that's essentially how your typical shapes are made. Okay, and I think this would be the real one. I think this is fine. So whatever the Yoda example I shown in the beginning is this. Okay, so you have this kind of affordable 3D printers. These printers today cost you around 15,000, 20,000. A decent one costs you with this thing around 30,000. Okay, you can, and it's ready made, you can use it. Okay, so these are the printers. So what happens is the wire, you can see here, is coming in, going through the nozzle, okay, and then being extruded in the molten form. You can notice how the shape is being deposited by the movement of the nozzle. So there is also a problem with support mechanism here. I think uh, so kind of, I mean, what happens is once you have, let us say you want to build a shape like this. Okay, so till now it's okay. You're putting one brick or another brick, etc. is fine. But what happens here is this is a overhang feature, what we qualify as a mathematically overhang feature or a negative K ratio. Okay, so how do you get these kind of, so what happens is the moment you are trying to deposit material here, it does not stay there, it just simply falls down. Okay, so typically what do you do in civil engineering? You put scaffolds. Okay, so you have these scaffolds, and then you put the concrete on it, and then you remove the scaffolds. Okay, so similarly, even in 3D printing also you have this. For example, you see for this wing, they have this black color material too. Okay, so what you are doing is you are putting another material, which is a sacrificial material or a support material, how we call it. Okay, and if you are going for high end printers, little costly printers, this support material will be even water soluble also. Okay, so that means you will make the support material through material 2, actual one through material 1, build them together, put it in water. Okay, the support material gets soluble, removes and goes on. Okay, so that's kind of how you can imagine your plastic printing being done. Okay, so another variant of this thing is your I think related to the current context. Okay, contour crafting or concrete 3D printing, etc. The idea here is it comes under the category of extrusion based 3D printing. Okay, what you are doing is you have a nozzle and you are pushing the material through the nozzle. Okay, so all the plastic as well as concrete, etc., or even biomedical many times comes under the category of extrusion based 3D printing. You have a nozzle and you are pushing the material through the nozzle. That's the basic paradigm here. Okay, and you can make a lot of these complicated shapes. Even pottery and clay modeling, etc., is also being popularly done using these processes. I think this I will not spend too much time. This is what you're going to see a lot more better examples of it. Okay, but the bigger one is all of that comes under your material extrusion category. Okay, the third method is what we call as wet polymerization. So here what we do is kind of take sheet and take a polymer which is photosensitive, selectively pass light and convert it from liquid to solid. Okay, so typically what happens is you have a tank which is filled with photopolymer resin, and selectively you are putting the laser and you are then converting from liquid to solid. Okay, so this is kind of, I think, how the process actually looks like. Okay, you can see a small laser dot. Okay, that is actually your laser which is moving to the desired place, and then that laser spot is converting the liquid into solid by photopolymerization method. Okay, and what happens is after that you kind of go on building. Okay, and you lift up all the remaining things which you don't want to be, this thing is liquid state that flows out wherever the laser has passed, that becomes solid. Okay, and you finally get the solid component. So most of your dental implants these days, dental fixtures, etc., are actually being done using this method only. Okay, photopolymerization method. Okay, so you have this fancy dental, not implants. Implants are metals. Okay, but fixtures and coverage, etc., are all done using these methods today. Okay, you can make a lot of complicated objects. You can even make casting patterns or lost wax patterns to create solid materials also. Okay, so and even jewelry industry. Okay, so all these are essentially made out of wax. You can use them as investment pattern for creating gold or silver ornaments also. Okay, whatever are fancy ornaments, they're also being such complicated shapes can be directly 3D printed and then used through the investment casting methods for gold ornaments or silver ornaments also. Okay, so then the fourth method is your powder bed fusion. So here what you do, it's a little variant of your powder metallurgy. So what you do here is take a simple material in the powder form, okay, and have the laser sinter it. You can see essentially wherever the laser is going, the loose powder is getting sintered and boxed together. Okay, so it is kind of, I mean, fusing together into a solid. Okay, so the remaining part is all loose powder. Okay, and wherever the laser is passing, it becomes solidified. So in this fashion, you can go build a component. So you just remove all the unsintered powder around. Okay, and finally, what you have is your component you are looking for. Okay, so the idea here is you take metal powder, sinter it or fuse it with the help of a laser or an electron beam, etc., and you make it into the actual component. Okay, so there are different ways of doing it, different methods of doing it. Okay, so this is what is happening. So this is your loose powder which you are spreading as a layer, and the laser is fusing the powder particles together into solid. Okay, so that's kind of the basic technology of the process. And different applications are there, very complicated conformal cooling ducts can be easily made using this process. Okay, or you have channels, for example, internally through like this. Okay, or even biomedical implants. Most of the biomedical implants, your knee implants, your other hip implants, etc., are all manufactured today using this process. You can actually make print pure titanium implants using this process. Okay, so most of the biomedical implants use this setup. And you have very complicated shapes like this, lattice structures or periodic structures, what we call. Okay, can also be 3D printed. Such kind of periodic structures can be easily achieved using these processes. The fifth variant is a similar concept. It is just that instead of using a laser to melt, what they do is just glue to join. Okay, so these two processes are very similar, except that here you are actually melting the powder. Here you don't care about melting it, you just use a glue to join the powder together. Okay, and the advantage of it is you can actually do color glue also. So once you are starting spreading glue, you can have a color glue and have a multicolor objects also manufactured. This is JetCorp is one of the initial ones which has developed such a process. So it can help you. So in the initial days, what they used to do, they used to do starch powder for the raw material and normal. So they used to say literally, sir, up, you can eat this. Okay, so that's also possible. So these kind of different multicolor objects also can be manufactured. The reason is essentially what you're doing is using a different color binder for achieving it. Okay. Okay. And then you also have the material jetting. So similarly, what happens is instead of adding the glue, you are adding the material directly onto the object. So this is kind of your multi-jetting. Okay. So the add-on material using your HP, your normal printer material, you go on adding material and build the component in the desired shape. Oh, sorry. Oh, jumped. So this is typically what happens is you go on spraying the material in micro droplets. Okay, so this is typically what you call as micro droplet spraying. So you spray the material in micro droplets, but hundreds of them in an array. Okay, and then you get the final desired geometry. You can even get what they call as digital materials here. You can even have transparent, translucent, multi-material, different hardness, different softness all together also possible here. Why? Because you are using different nodules for each of them. Okay. And the final one is what you call as your directed energy deposition, DED. So this is, in this what happens, you have powder coming from separate nodules and you have laser coming from the center and centering the powder. So this is kind of one of the technologies we also actively work. This is ideal for metal high application, high-end application, metal applications. Okay. So all this, okay. So you can see essentially the metal powder is coming from the 4 concentric nodules, and that powder which is coming is being sintered by the laser which is in the center. Okay. Of course, there are different technologies. There are concentric nodules. There are full circular nodules, etc., etc. Okay. But the idea is you have powder being sprayed. Okay, and the powder is then fused together with the help of a laser. Okay, so that's kind of so literally you are very similar to your laser cladding. Okay, and these you can do repair applications, functionally gradient materials, high-end applications, etc., using this process very easily. Okay, and there are various of it. Some use laser, some use electron beam, some use arc, some use wire, some use powder. Okay, so different technologies exist, but the concept is you have the raw material and the energy source moving together. Okay, now I think kind of these are the various processes what you have. I'll just shift the gear a little. Okay, uh, so talk about a little on what are the various pedagogical related things which are happening in related to additive manufacturing at IIT Hyderabad. Uh, so this kind of I think we also have a course called digital fabrication. This is a first year course meant for all first year BTech undergrad students, computer science, electrical, mechanical, civil engineering, everybody does that. Okay. And the idea here is to give them a glimpse of 3D printing. So kind of the irony or the unfortunate thing here is all the BTechs of IIT, they know CAD modeling and they know 3D printing, but only a handful of our master students know. I think if I ask my own students, they may be 50-50, sir. Some of them know, some of them don't know. Okay. So anyway, I mean, but at least thankfully, all the undergrads of IIT Hyderabad go through this course, are familiar with CAD modeling and 3D printing techniques very detailed. Okay. So kind of, I think, we cover them CAD modeling, 3D printing, and this is a course we teach it for 400 students, 500 students in a go sometimes. Okay. So we have a large number of 3D printers, large number of, so in fact, many times the course is more of logistic planning than teaching. Okay, so to do all that. Okay, and these are some pictures from that old era. Old era because you can see me here. You cannot recognize me unless I tell you so because kind of, I mean, I used to have a lot more black hair at that time. But yes, that's me. Okay, so and why I was putting this thing is also uh, I've done my BTech in IIT Madras. Okay, and 2 semesters of AutoCAD, 1 semester of ProE. Okay, 3 semesters of CAD modeling alone, and another 3 semesters of drafting also. Okay, so literally I have done 5 courses or 6 courses only on drawing, engineering drawing. Okay, and here I was trying to propose that look, that 5 courses will do it into half course. Okay, and the first thing which people were thinking is not that it is impossible, but this fellow is not going to do it thoroughly. Okay, so kind of, I mean, they don't do a thorough job of it. They'll just casually teach. Okay, but it is not true. Okay, why it is made possible is not because I am a genius. Okay, but because the technology matures. Okay, if you see, for example, how you remember, you're young, but ask your little elder brothers during some 20-30 years back, learning computers means going for a different this thing, a different lab will be there, a different computer course will be there. Okay, and I mean, eh, learning programming is a big deal. Okay, and if people used to get just for learning C in 6 months, you will learn C and you will get a certificate in hello world, and you make claps about writing the first hello world program, etc. Now you see, cool kids are doing. In fact, my daughter has AI as a subject. I don't know whether to be happy or sad about it. Okay, but the point is, as the technology matures, it simplifies also. Okay, so similar thing has also happened with 3D printing. General fabrication is, as the technology has matured a little, okay, it has become easy for us to actually implement and cover the same content in much simpler manner, in much effective manner also, but with a lesser time span also. Okay, so that's something we are doing. So these are the exercises my students do in our class. Okay, and these are actually components which they built in that course. First year students do that. Okay, and our research, I just wanted to kind of, so we also work on metal additive manufacturing, personal I do. Okay, so our area is on the large metal additive manufacturing. Okay, so we have various facilities to do that. Okay, and I think this is one of the videos we were showing. So this is like a 3 meter component which we were able to successfully build. This was part of a DRDO project we were doing. So again, the idea is just like you've seen in the plastic, build layer by layer. So currently, I think this is one of the biggest, not one of the, this is the biggest 3D printer, at least in India. Nobody has done bigger than 1 meter or 1.2 to my knowledge. Okay, so kind of, we are able to do demonstrate successfully 3 meter large components also. Okay, and another few samples, etc. What you have done. Okay, now I think let me summarize. Come back. Okay, as I said in the beginning, the intent of this session is only to give you a brief roadmap, a overview of all the 3D printing processes, and also a little philosophy about them. So typical questions people keep asking: is it cheap? Is it fast? Is it accurate? Is it metallurgically good? Okay, so definitely the bad news is it's not cheap and fast. Okay, for example, this pen costs you 10 rupees, 5 rupees through injection molding. You can make in 100 in 1 minute. Okay, it takes you at least 3 hours to print it and at least 100 rupees to do it by 3D printing. Okay, so it's neither cheap nor fast by the conventional techniques. Okay, but then again, you have to also look at how you are comparing it with the process planning also. Okay, so typically the corollary is again very similar to your 2D printing corollary. Okay, if you want one thesis of your one copy of your thesis printed, you'll go to a printing shop. Okay, normal Xerox and printer. Okay, शादी का कार्ड छपवाना है और पैम्पलेट छपवाना है. What would you do? You'll go to your offset printer. Okay, the idea here is offset printing. Okay, has a lot of setup cost. For example, I mean, if you gone for some marriage cards or other things, okay, that person will charge you 2000 or 3000 just for the block of it. Okay, there is a block printing, and after it, they don't even charge you 2 paisa or 5 paisa for example. Okay, whereas your normal laser printer costs you 2 rupees per page. There is no setup cost, there is no offset printing, etc. Okay, but also the time. Okay, it takes, for example, sometime 2-3 hours to set it up. Okay, here it's uniform. So similarly, the same concept also applies for you in the 2D printing, 3D printing also. Injection molding may take only half a second to do this, but to create that injection molding setup, it requires 2 months for me. Okay, the injection molding setup is not easy. A plastic molding setup is not easy. Okay, that setup, and then 2 months plus 10 seconds. Okay, versus 4 hours. Okay, so which is faster? So the answer depends on quantity of it. If you want 4 numbers, if you want 10 numbers, 3D printing still works out to be cheaper and faster. But if you want hundreds of numbers, if you want some 10,000 components, 3D printing is neither fast nor economical. Conventional methods are more effective. So, okay. So 3D printing is ideally suited for low volume production, not for high volume production. For low volume production, it is very good. For high volume production, conventional methods are still good. Okay. So low volumes, it is definitely cheap and fast, but for high volume production grade, it is not. Okay. And is it accurate? It depends. Okay, I mean, so for example, same, is a 3D printed bridge accurate than a mason's work? Probably never. Okay, but I mean, हर कोई ताजमहल नहीं बना रहा ना. Okay, it's not that everybody wants to make a Taj Mahal out of everything. Okay, does it have necessary accuracy for be structurally integrity? Yes, in most components, yes. Okay, so that's all we care. Okay, so is it metallurgically good? Similarly, okay, so kind of, I mean, so the idea is it best? At least not yet. Is it adequate for compliance purposes? Definitely yes. Okay, so that's kind of how we are looking at it. Okay, so I think judge things in that perspective. Okay, so it's not necessary that every component is a high-end component, is kind of, I mean, very, very rare component. Okay, mostly compliance requirements essentially user defined, are they meeting or not? In most applications they do. Okay, so kind of, I think, so mostly 3D printings are maturing as an industry and a technology. Okay, and you have a lot of this easy. So 3D printing is one of the few places where you have a open community. So typically software community has a very vibrant open community. Okay, so for example, all your Linux, your Firefox, all this came out of free open community. Okay, 3D printing is one of those rare things, the hardware arena, which has such a ecosystem. Okay, so and you have a lot of these examples. You can go download them for free. There are nice videos how to assemble. There are even freely shared CAD models which help you do that. Okay, so you even have some of these medical printers. So in the peak of the COVID, so what NIH, okay, American one, okay, what they've done, they've just shared they created the CAD model and shared complaints related. Okay, and then you can print your own model and use it. Your own mask you can 3D print. Your own face shield you can 3D print, etc. Okay, and so kind of, I think. So these are examples of how 3D printing can also demonstrate its value beyond basic hobby also. Okay, so I think there are various ways in which, so there are even examples of how you can use 3D printing for visualizing mathematics, how you can use it for different shapes, etc. Okay, so I think coming to the bigger context of it, okay, major takeaway I would say, see, mass production, I don't think it is a game India is going to win against China. Okay, I mean, everything said and done, kitna bhi fight maar lo, nahi hone wala. Okay, because if you actually see, China is damn good in the mass production. But at least where our strengths are, Indian strengths, kind of, I mean, service industry, Indian industry has always been, okay, compared to the manufacturing industry. And the future of manufacturing is going to be not mass production but mass customization. Okay, so I think that's where people are going. People don't like uniform watches, uniform mobiles, and uniform mobile covers also. Okay, सबको हर किसी को unique mobile cover चाहिए. Okay, that's the trend of the day. Okay, and that's what we call as mass customization in the technical words. And mass customization is actually a combination of both production and service. Okay, and can India take a lead there? Okay, at least in the evolving fields, future fields. I think that's where the potential is. And I think, I mean, kind of, so additive manufacturing is the ideal technology for achieving it. Okay, so one of the advantages of additive manufacturing is it is the ideal technology for facilitating mass customization. Okay, so this is just an idea I would leave for you to think on also. Okay, and with this, thank you, and any questions or any inputs are welcome.
See, there is a opposite to manufacturing.
Yes. So composite additive manufacturing typically comes under extrusion based 3D printing. Okay, so what they do is take a clay slurry, just like you are doing cement slurry. Clay is extruded through the nozzle. Okay, and that's how you make. This is typically the clay kind of composite, but the HBDA, the dental kind of composites are comes under SLA methods. Okay, what you call SLA, photopolymerization methods. Okay, so these two are the methods available for ceramic printing today. Okay.
It's usually discuss also.
Oh yes, of course, they do. They do. High temperature crucibles, etc. They do that. Okay. Yes. Okay, I think in the interest of time, I'll stop here. Okay, and you're always welcome for any questions, any these things. Okay, and I'll stop here. Thank you.
So, a few things we do have fantastic facility for rental manufacturing, and as you've probably seen, rental manufacturing is the bigger umbrella that is we put ready for extrusions, ready for taking. The one that's more convenient is unit from what we enabling or locally calling as 3D printing. Depending on the task we have, we are session on the process by which you will need access to Wi-Fi. Edu works here. So if you have an Edu podcast, please use Edu to log into Wi-Fi. Otherwise, there is IT Hyderabad guest account. The password is given in the the account itself, or if you look at the email, the net ID that itself doesn't work. Okay, I believe it's ID and check 20. If you like to
Wood block printing is 280, and then jumping to wood and metallic ceramic printing, lithography that all of you would have heard, that lots of ancient empires used to do their own artistic stuff. Color printing started in the 1800s, screen printing 1900s, photocopiers became common in 1960s, and then a whole series of printers that we use for common applications, dot matrix later, and then 3D printing around 2010, mostly do the plastic extrusion kind of things. Again, same thing that he talked about. Dr. Surya made it to 7 different types. Here are 5 different types. Again, depends on who you ask. Different types of 3D printing, right? You have a printer, you have a material that you need to print with, you have the shape that you're printing, depending on what is your final application that you want. So that's what it is. So 3D printing or additive manufacturing, one of those techniques, as opposed to subtractive manufacturing. There's another thing with subtractive manufacturing. So if you see a carpenter make a wooden object, it's subtractive manufacturing. They take a block of wood and they carve a piece, carve the shape out of the wood by removing piece of wood. Or a sculptor doing a stone sculpture is subtractive manufacturing, where you subtract things. Whereas we are talking about additive manufacturing, putting things together. So additive manufacturing, that's what Professor Surya was talking about, layering things one on top of the other. Subtractive removes the material. Some of its examples for additive was subtractive manufacturing. A little more repetition of what you've seen. Again, types of additive manufacturing, you saw all of this in the previous slide, so I will not go through it in detail. We'll get into more of concrete things. Binder jetting, one of the additive manufacturing techniques that you saw earlier, is used in, I wouldn't say structural engineering, but kind of civil engineering, soils, for example, right? You use binder jetting using sand and soil to create soil and sand structures, not structural shapes, but things that you can use with soil. So binder jetting is also one of those things that they use. Extrusion-based additive manufacturing, that's what we're going to spend a lot of time on. That's your chocolate molds that you make of the pasta that you see is actually an extrusion made. So if you see this shape of pasta, if you go to a restaurant and get it, that's an extrusion-based food product that you get. Architectural structural shapes, you can get lots of different structural shapes. And one of the things that in civil engineering, structural engineering, that you get with additive manufacturing is the flexibility with structural shapes. As civil engineers, you all know that shapes are important, right? But we are all restricted with the kind of shapes that we can use. Prismatic shapes is all that you've learned. You probably have learned 3 classes on reinforced concrete design. You probably designed only rectangular beams and at most rectangular and circular columns. We never did any other shape. We also learned ever since our first class in structural engineering materials, concrete is strong in compression, weak in tension, but we have steel comfortably to put in concrete to make a reinforced concrete structure, tension, compression taken care of. But in the process, what we do is we put a lot of concrete in places where we don't need anything at all, right? We waste a lot of material. So now, with a sustainability angle, we don't have enough resources to make large structures. Countries are developing at such rapid pace. India is developing, China is developing, Africa, tremendous development. Where do we get all this concrete from? And even in India, if you look at it, you don't have enough sand now, right? You have paucity of sand. Natural resources are at a premium. So to conserve resources, concrete being one of the most used materials in the world, we need to conserve resources. We need to make sure that we need to put material only where they're actually needed. So along with shape optimization, you can do the structural optimization to put concrete only where we need them, not put randomly. For example, if you do a reinforced concrete beam, you say that below the neutral axis, concrete does nothing, right? It's all the steel that does if it's a simply supported beam. So in those kinds of systems, can we do the shape optimization? Can we do? So the bridge that Professor KVLS has printed here, shape optimized to make sure that you put concrete in only the places that you need. That's another major advantage with concrete additive manufacturing. So if you're thinking of building another house exactly like the house that you have, a rectangular shape and building, probably not much of use. But if you want to use a unique shape where you optimize the material, you optimize the geometry, you can save 30-40% of material, you make the structure work harder in locations where you want it, this becomes a useful technology. So you see lots of different shapes, lots of different architectural shapes. That's a seating chair kind of a bench kind of a thing. A wall geometry. You can save a lot of material by doing a wall geometry. You can have bracings for the wall like this, and you can have thinner whites for walls. If you're building a concrete wall, you can actually start to save material. You can also shape the wall in different ways to do unique structural functions. Probably later in the class, in the session, we'll see that as well. So that's concrete 3D printing. This is one of the bridges that was built in Europe some time ago. Another picture of how you can actually shape a building in a unique way. AI is everywhere, so I thought AI can also generate some 3D printed buildings. So I asked AI to generate a 3D printed city and in concrete. So it actually created a concrete ball first and built city on top of that. Maybe it thought Earth also can be made of concrete, right? AI's imagination can't question. Automation. The other advantage for 3D printing, again, so all of these are advantages that we have not completely made use of yet. Right? So these are all potential advantages that we all can make use of in situations that we can make use of them. So these are not technologies that are show me a 3D printed structure that is like this. No, you won't find it. Right? Somebody will have to build it. It has to develop. But automation has created lots of advances in civil engineering profession, especially in the Western world where labor is ridiculously expensive. In locations where labor is cheap, this might not seem to be such a great advantage. But in the US, for example, where if you have to spend $1,000 on something, for example, if I have to do, so I learned a lot of things that I would have never learned if I were in India. For example, I can do reasonably good level of plumbing at my house. Okay, I can fix reasonably decent stuff. I can fix garage doors when it's broken. I wouldn't have done this. The reason I learned it is if I call somebody to fix it, he'll come only a week or 2 weeks late, right? Because he's so busy, they have so much of work. And then he'll charge me an arm and a leg to do something so simple. Even to just come in to look and tell me what the problem is, that's $150. So expensive. Labor is so expensive, and specialized skill labor is not very easily available. So if you are a plumber, there are in Australia, for example, lots of students who went to study business and marketing are not getting jobs after their 2-year degrees. And what the Australian government is telling them, look, you're not going to get these jobs. We will now pay you 6 months if you're interested to join a skilled labor course, carpentry, plumbing, masonry, we'll pay you to do it 6 months to do a course, and you can stay back after you doing your MBA. You can be a mason, for example. You'll actually get more handsomely paid. Do you want to do that? That's what Australian government is asking lots of foreign students who are going there. So automation is such a handy thing when you don't have people to do the work. And that's another one thing. And in the US, budget overruns and cost and time overruns are standard in every project, right? So how do you control that? Can automation control some of that to take care of dull, dirty, and dangerous? That's not a really good politically correct word, but this is what they do. Dull, dirty, and dangerous rhymes also nicely, right? You can say D, it starts, all three starts with D. And these are things that you don't get people to do the work. Can you automate them? Benefits are there. There's lots of money spent on safety, on worker safety, right? One life lost is a life that's you're never going to get back. So there's no value that you can put on life. Of course, there's insurance companies that will pay you whatever amount of insurance for the life loss, but realistically, you can't put a value to life loss. So safety is paramount. So any minor accident is treated as a major thing, and companies and construction companies take pride in saying 1,000 days without an accident. You'll see this big boats in, if you go to construction sites, 1,000 days without an accident. So all of that. So those are critical. So all of those benefit from automation. So if you can make construction automated, the downside is in a country like India, a lot of people rely on construction labor, right? So you're taking a lot of labor off. But again, I'm talking about situations where you don't have that. Automation is a good thing. Construction productivity has declined. This is World Bank's report. In all fields from 1990s to 2020s, if you look at it, productivity has increased. Construction productivity has come down. There are several reasons. You can't just blame the people for that. There are several reasons for why that is. But pretty much every other industry, you see an increase in productivity, whereas construction, lack of productivity. How do we account for that? Again, same idea here. Industries like media have seen the most digitization productivity growth. Construction is at the opposite end of the spectrum. If you look at digitization score, very low digitization score, very low growth rate, very low growth rate, right? So how do we make, so one of the ways to make construction more of, if you think of construction as a manufacturing process, if you could think of constructing things as a manufactured process, because quality for a prefabricated product, for example, right? The quality that you require is like a manufactured product. So can we make these processes better? Lagging construction productivity costs the global economy $1.6 trillion a year. Can we correct some of those changes? And look at in North America, lots of, again, it's all driven by numbers, are American numbers mostly, so driven mostly by North American numbers. So three primary opportunities in digitization generally: automation of traditional physical tasks, like I talked earlier, robots laying bricks. In the 1970s, it was done. Machines paving roads. Every road is paved by a paver, right? If you look at massive highway developments now, you have concrete paving machines paving it, asphalt paving machines paving it. People don't pave it anymore. It's automated already, right? So you're doing it anyway. Rebar tying of rebar. So there was some study that was recently done in the US, and simply on a 1 mile of a concrete pavement, removal of rebar tying, the labor associated with tying rebar alone is $2 million worth of saving. Labor in a mile. So hugely labor intensive processes. Automation of modular construction production factories, including 3D printing of components. Can we do it? And there are ways in which, for example, can we do 3D printing of components that are repeating over and over again? And then digitization, automation of design, planning, and construction procedures. This is where the industry wants to reach. The entire digital construction industry wants to get there. The whole process, including design, planning, and construction. So there is this whole report that was put out by a digitization committee uh, called democratization of construction. You basically say that I want a house of this design. Your CAD generates it. You can take it to a potential, probably 2050, 2070 year futuristic plant. You can take it. The robots will design that building. It'll be printed. It'll be given to you on a platform. You can take it on a platform and put it where you want. That is the dream of how you want the entire building design and construction process to happen. We are so far away from it, but at least some thought processes. So what they eventually want is integrated design and manufacturing and assembly, process innovation, optimized improvements, product innovation. So look at your constructed output as a product, right? So if I have a building, what are the components? I have walls, I have beams, I have columns, I have roof, I have my functional elements, plumbing. Look at each of those as individual products. And how do I improve the design, construction, and production of those individual products? That's the whole idea. And eventually, affordable, zero energy, healthier, uh, improving productivity, quality, affordable. So this is all the big picture where the industry eventually wants to grow. Several industry groups are putting out white papers as to how they want to see this in the next 30, 40, 50 years. And we are really at the starting point of it, and really learning to walk the walk, while in lots of other industries, additive manufacturing has progressed substantially, right? One of the major things, and Dr. Surya hit the nail on the head, right? If you really can't make something economically, as a civil engineer, you will know your product is not going to be sold. Nobody in the civil engineering industry wants an expensive product. You want it economically. In a mass construction, there might be niche consultants, niche clients who would want it, but generally, unless you're economical, then what's state of the art? You're not going to make headway. Or your product should have such unique qualities that you should be able to make use of. And so the way that you do in 3D printing, the way that you can actually make it economical is to save materials from a conventional construction point of view by doing all the optimization, for which you need to understand how to design, what are the properties of the material, where do you put it, how do you put it. So it's going to be a collective process. Here is how the life started. 3D concrete printers, if you look at it, this is where it was 10, 15 years ago, and we've come such a long way now, from really people printing mortars or paste in a very small form. We also have done it. That's the process. That's evolution. This was the first printer that I bought. Again, a 3D printed 3D printer. Every part of this is 3D printed. That was, I don't remember how much. The company is out of business now. They don't even make it. It was an extrusion printer. And then I don't even remember the number of. So we got, in the university, I was buying these syringes like crazy for printing, right? And our business office came and questioned. They were thinking I was doing some drug business in the lab on the side by buying massive number of these syringes, these barrels and dies. So this was what we started with, but we've come a long way. There are now very fancy printers, robotic arms, gantries, all of those that you can do. You can have extrusion-based printers, you can have frame-based systems, robotic arm systems. Frame-based is your gantry ones, robotic arms is the one that SimplyForge also has. If you go to the field trip, you'll see that. There are several different types, the cable robot and concrete extruder. This thing was there. Oak Ridge National Lab in the US came up with this very nice cable controlled one that could do it, but it wasn't really popular. Icon is this company in Texas which actually built about 200 houses, 3D printed houses in a big 3D printed park. and the company is almost going out of business after doing all of that. But they came up with their 3D printer called Vulcan, which is a gantry system, but a much more bulkier version. It's a very unique kind of a system. Apriscore came up with this thing where you can have a kind of a space thrust kind of thing that prints concrete. Um, this was the older version of the robotic arm that you can see here now, much more sophisticated, much more complicated at the edges. But if essentially what you're doing is you're mixing whatever you want, you're putting it in extruder, pushing it out, and then eventually it comes out on the side, and you want to build it, layer it, print, layer on top of it. And you will see that if you want to print concrete, conventionally we use formwork because concrete is a flowable material. It flows, it doesn't retain its shape, and therefore we need something to contain its shape until it sets and hardens. Now we have the requirement that as soon as it comes out of the nozzle, you want it to be shape stable. And then not just shape stable, you want the layer to be printed, you want the next layer to be printed on it quickly, you want the layer on top of it to be printed quickly, you want to be adding superimposed load very quickly. Whereas in the conventional set, you will say you put the concrete and go home and come back after 3 days or 7 days or whenever you want to put the next load on top of it. Now the loads are added instantaneously, which means the structure should have the strength to carry the superimposed loads without collapsing, which means the fresh state properties of concrete will start to control a lot of what is happening when you print concrete. Unlike plastic, where as soon as it extrudes, you will see that you would have seen pictures where it solidifies. You are applying heat to solidify it, right? Or you're applying some kind of a thermal impulse or an optical impulse, a light to solidify it. Whereas you don't have the flexibility to do that. You can't take a giant heater and go right next to concrete. Even if you can take a giant heater and put it next to concrete to make it set, it will give you lots of other problems as you go through. So you really don't have that option. You need to make the material itself do that process. So you have to control your hydration, you have to do all those. That's what we will spend a good amount of time, probably tomorrow, on how do you control the early age property. So that's pretty much what it is. That is aggregate bed concrete printing. This is something that's coming up now. So you basically put a layer of mortar and then you just layer some aggregates. The next layer comes in. So you can, people complain, oh, concrete 3D printing, you're printing only mortar. It's not even concrete. No problem. We'll make it concrete this way. Unless if you have a printer with a nozzle that is large enough, with a blade that's large enough that can handle aggregates. Now there are printers that can handle 10 mm aggregates fairly comfortably. The problem is that the printed surfaces will look very ugly if you have aggregates. Mortar printing looks fairly nice. Again, going back to a few other concrete printers, and the price of those printers, you can see 1.8 million, $500,000 worth of well, some of them, of course, have come down a little. Cobord is one company that is, let's say, popular all over the world now. They have pretty much a good US market. They have lots of markets in Asia, in Southeast Asia as well. This is what IIT Hyderabad group has printed. This is the IIT Madras supported group. So again, you'll see this like little pockets in India coming up with collaborating with companies that manufacture printers, developing materials, and you'll see that. And it's actually in civil engineering, we really haven't seen this if you look at it, right? Where a technology develops from, you will see this a lot in computer science, you will see this a lot in electronics and semiconductors. Lots of semiconductor chip advancements have come from companies, Berkeley and Stanford. Those are the places where, if you look at Intel, Intel would have gotten the patent, but some of those fundamental technologies they would have taken from Stanford or Berkeley or Carnegie Mellon, places like that. Whereas in civil engineering, we do research after somebody figures out that they want to construct something like that. We pick it out and say, can we make it a little better? We are all about incrementally making it better, right? But this is one where it's fundamentally started from academic institutions and then has branched out in most countries. And most groups have places like this that they have worked with, right? So this is a cantilever column. You can see the layer by layer printing process that's being done. Lots of applications. Again, we have some castles being built. This is the U.S. Army Corps of Engineers built this soldier huts kind of things. They did this in about 2015-ish, so about 10 years, 10, 15 years ago. This is IIT Madras's first demonstration of a printed building, but this was printed in about 4 or 5 different pieces and stacked like you do bricklaying. This is again another U.S. Army Corps of Engineers project. This is I think it's somewhere in China. They've done this, and lots of examples uh, of uh, of printing. This is the first house that we did in Tempe in 2018. This is the first permitted house in the US. Permitted meaning a city approved construction of a 3D printed house. Until then, there was no permitted houses. So you're not, if you can build, but if you live in a house that's not permitted and something happens to you, no insurance company will cover you. And if you understand the situations of living in the US, if you don't have insurance, you better run away to somewhere else, right? So this is the first permitted house that we built in Tempe. This is built using a cobalt printer. This house, it's about an 1,800 square feet house built by Habitat for Humanity for a family that registered with Habitat for Humanity about 5 or 6 years ago. And among the families, there was 200 families, homeless people registered with Habitat for Humanity. And then when they said we are building a concrete house, nobody wanted to live in that concrete house. Everybody wanted their traditional wood framed house. US, it's all wood framed houses, right? They wanted only the traditional wood framed house. Nobody wanted this house. And finally, they got a family to live. And this house was supposed to be built in Arizona in February, March timeframe. The printer had to come from Europe, was stuck with customs in Texas, did not get to Arizona till May. In May, in Arizona, temperatures go to 40 degrees Celsius. They were trying to print this at 40 degrees Celsius, and in 4 layers, the whole thing is cracking left, right, and center. Right? So then we had to go in and do lots of testing to change the mix and to change the curing processes. But eventually, it came out decent. Again, remember, this is 2018. 2018 is infancy of 3D printing still. So you will see they're not very good. So inside was all plastered because the family who lived there said, we're not going to live there until it is all smooth and nice. So they had to plaster the whole thing. But eventually it was a nice experience. We did a lot of testing in our labs for cracking, for strength development. Strength was not developing. Because a city wanted strengths that are much higher than allowable concrete strengths because there was nothing in that. So they want to be safe. They said, without 4,000 psi, we're not letting you print. And then to get 4,000 psi on a mortar, which was cracking left, right, and center, was challenging. And this is the architectural drawing of that Habitat for Humanity house. This is the post office that was told by Professor Surya. This is in Bangalore. I think this is L&T built it with IIT Madras. This is Tosta built it somewhere in Chennai. This is the first house that IIT Madras built in their campus, but they have completely plastered it because this outside surface wasn't looking all that great. And this is, all of you know what this is, all familiar faces. The bridge right here in the campus. So for people who have not seen it, you're taking them there, right? At some point of time, you will see the bridge that's in the campus. And this is the latest one that Professor K.V. Ellis is claimed to fame. This is the Indian Army's thing that it was Was last week. It was the news last week in the newspapers last week. So beautiful tiger structure. Again, you look at it, if this again, by the time I cut and paste, it's not good. But if you really look at the computer, the nice features on the face of tiger is actually pretty good. And you will never get it in any other form, or you will have to spend so much of time to make a mold for it to do it, like Dr. Surya said earlier. Higher resolution, pretty good. Major advances. So they said we have to have 4,000 psi, but the wall, that the double white wall, was not supposed to be carrying any load. Every 10 feet, you had to put in a column, you had to put in rebar, physically put in rebar and grout it so that these are all columns. And then the walls are simply there. It'll take a lot of load. 4,000 psi concrete is 4,000 psi is what? Close to 30 megapascal. 28 megapascals or so. It will carry a lot of load, and walls 28 megapascal is huge, right? 15, 20 megapascal is more than sufficient for walls. But we had to do that for code. So that was your initial way in which you reinforced. Reinforcing still is a big unanswered question. We'll spend some time on the last day talking about some challenges. No real solutions, but some potential ways to take care of that. Solid geometry. This is such a solid geometry. Think of how much weight this will have. Think about that. If you build something like that with solid geometry, it's going to have tremendous mass. And how do you do it? That's a vertically printed panel component. So now you start to make allowances for hollow spaces in between and start to reinforce those hollow spaces. Because you really can't reinforce with steel, it's going to be very difficult. You try smart ways to reinforce it with grids itself while you print, that you can do in different ways. You make use of the geometry, you understand the load paths, print where the load paths are actually so that the load goes through that. You can do a lot of those things which you are not able to do with conventional print. Okay? All right. Before we get into real cement-based materials, any questions, comments, anything that you want to? Yes. Yeah, it was a concrete foundation. So foundation is all done. It's all concrete mat foundation. So just a concrete mat. In Arizona, because of the type of the soil, you always need a post-tension foundation. So it is always a standard way that you need foundations for that. So it's all post-tensioned. Other questions? All right. Is this pace good? Am I going too fast, too slow? Let me know if it's too fast. Good, right? Let me know if you need me to change the speed or whatever. Okay. Now, for concrete, what do we need? A few things we talked about, but kind of getting into the nuts and bolts of what it is. 3D printing by extrusion is what we're going to deal with. So forget about the remaining 6 different things that you saw earlier. Those are all important things for different materials. Right now, we'll talk only about extrusion. 3D printing by extrusion, layering through extrusion. That's what we do. What do we need first? The concrete has to be soft enough to be extruded, correct? You need it to be soft enough. Anybody who has extruded, anybody who helped your mother in making any of those South Indian delicacies, murka, things like that, if you've helped them squeeze through, you will know, right? You have to have it soft. What happens if you don't have enough water in that dough? You will have to put in a lot of force, and then whatever comes out will be cracked. So you have to have the material soft enough to be extruded and to intermix with the previous layer. Because if it is not soft enough, you've put one layer. If it's not soft enough, it will not really bond with the previous layer. So you have to have soft enough. But then once it is soft enough, can it support the previous layer then? No. But then what you need is to have the property development fast enough to be able to support its own weight and weight of the superimposed layer. How do we do that? And that is the whole idea of playing around with rheology of concrete. So lots of people who work on 3D printing of concrete or who has to do anything with 3D printing of concrete will spend invariably a lot of time with the rheology of concrete, very similar to what people did when they started to pump concrete 20, 30, 40 floors above. Right? You can't carry the concrete all the way. You had to make the concrete fluid enough in a way that when you get to the 30th floor, still you are getting the paste and the aggregates as one homogeneous mass, not the paste coming first, the aggregates following later, or vice versa. Right? Lots of advances in admixtures happened because of that. Lots of advances in pumping technology. What happens when you have high shear flow within a pump? We never had to do that with concrete. All you had to do was mix in a mixer and place it right there. You never had to know what happens when you pump concrete through long distances, right? Pumping high shear flow. The whole idea of shear flows came through. We will use all of that in our understanding of how you can 3D print concrete. Finite waiting time between layers. If I can print one layer and go home, come back and allow it to develop strength before I print the next layer, then if I have 1 centimeter or 2 centimeter thick layers, by the time I build 3 meter tall wall, it'll be 6 months, right? I could do something else. So you can't afford to do that also. You have to have a finite waiting time. The waiting time has to be a shorter period. Yield stress change from layer to structure. We'll talk about the idea of what yield stress means. You would have seen yield stress, yielding when you did the experiment with steel, tension test on steel in your undergraduate class. You would have seen the yield stress, right? Fresh concrete also yields slightly differently. We'll see what that is. Rate of build-up. How quickly can you build layer after layer? How much time do you have? And that is now something that's intricately linked with the process. So if I have to build a rectangular shape, I need to know how big of a perimeter I have and how fast I can print, so that by the time I come back to the original shape, original location, a certain amount of time has passed by which the initial concrete that I have laid has some strength to carry the next layer. You see that? So your printing path, how do you adjust the printing path? If I'm building building a building with several different walls and all of that, what path is the optimal path for me to do it, so that when I come back after one layer of that whole thing, I'll be ready to print the next one. I can't be too quick because this one will not take the load. I can't be too late because this would have dried so much that there won't be good bond. Right? So again, questions that we have to answer. So lots of open questions that you have to think very differently from how you would design. Again, some more pictures of what it is. But think about the mixing process, which is happening within the printer. And then all of this is condensed here. So you're taking away all of these steps, right? This sequential process, laborers, tools, doing this whole process. Plus, eventually, less waste because you have designed it correctly. Your computer is doing it systematically. Process steps involved. This is some of those. You have to do the design, 3D model developed using CAD software. Different 3D printers come with their own software, their own ways in which you can do it. Several open source programs are available that you can go and do it and interface with your printers as well. Slicing is a process where the 3D CAD model is broken into layers so that the computer knows that it is a 2D that it is printing at one point of time. You print a 2D, you keep on adding layers to it and make it into a 3D structure. And then, of course, the printing involving file transfer, processing, and printing of design layer by layer. Again, even with your plastic printer, desktop small printers, you do the exact same process. No different at all. Post-processing, of course, curing, surface finishing, and finally you get the final path. That's your 2D path. Software will add paths on top of that to get to layer stacking to get your final object. Advantages, like I said, geometric freedom, flexibility, design ideal for architectural elements, reduction of construction time, labor demand, formwork free construction. This is another big advantage. Otherwise, if you want to build a concrete wall, you have to have a formwork, right? And then you pour the concrete inside the formwork. Now, the formwork, if I want a curved wall, I want to go and make a curved formwork. That curved formwork will probably cost me more than the concrete and the wall all put together, and more time, right? I have no design freedom. Whereas here, you will get a lot of design freedom. Topology optimization, you can optimize in whatever way you want. Challenges, limited reinforcement strategies. In your conventional concrete, that's what conventional, pour concrete over top of it, you're done. But now when you're printing, how do you put rebar along with it? That's a challenge. Layer interfaces and anisotropy. You remember that your first assumption when you studied your concrete class was concrete is homogeneous and isotropic. Both of these out of the window now. No more homogeneity, no more isotropy, right? It is okay. It's not a bad thing. Aerospace guys, you ask aerospace guys, nobody deals with isotropy at all. They love anisotropy. They design an aircraft structure fundamentally knowing that they need anisotropy. Composite anisotropy is what they use to get the right properties in the right directions. So it's not something that is not undoable. But the design standards that you have, the codes and specifications that you have, everything is all homogenized around the homogeneity and isotropy idea. To overcome that, it's and exposure performance. There is no reason why 3D printed concrete will be less durable. There's no reason. Of course, there are more layers, right?